Please, our next speakers, Dinesh, Will, and Sam, if you would. This is really the perfect follow-up to that particular presentation.
I hope so.
Yeah, yeah. So are we bringing...
Towards the end of the demo, maybe, yeah.
Okay,
Towards
all right. You guys have this choreographed already?
Yeah.
Okay, so Dinesh Jayaraman is at the University of Pennsylvania. I love the name of your lab, Penn PAL, for Perception, Action, and Learning at Penn. And I guess Will and Sam, your students, will be joining at some point during the course.
That's right, yeah.
Okay, so here's Dinesh, and we're going to learn some more about robotics.
So, thank you, John. All right, so I'll be talking today about how to train your robot. And I, too, wish that I'd heard Aaron's talk before I made my slides. But you'll have to bear with me. I am, after all, only a scientist, and we are not known to be good communicators, as you know.
But you can get better.
Yes, I will. The next time I do this is going to be a better slide deck. But I do hope that you will get out of this some sense of the excitement in my discipline, which is robot learning. So I study how machine learning-based techniques can be brought out of our screens and to real robots that actually work around us and help humans in our habitats, right? And this talk will start at a fairly unusual place for a robot learning talk with René Descartes' views that really gave voice to a commonly held belief up until only about a few decades ago, that the mind and body are two completely different things. So here Descartes says the mind and body are two fundamentally distinct entities. The mind is capable of thinking, but not of much more. And the body is capable of moving, but not of much more, in almost as many words, right? And Descartes' mind is divorced from the body. And science today has come to a consensus that says that instead, the body is really central to the mind, right? I like to bring up this story of the active kittens and the passive kittens. This was a study that was performed at MIT in the 60s, where these cognitive scientists, Held and Hein, took a batch of kittens at birth and separated it into two sets at random. One set was called the active set, and the other was called the passive set. These kittens were all raised exclusively in the dark, except for 1 hour each day. And for that 1 hour, a kitten from the active set would be tied to one end of the carousel from where it could control its own movements. It still had access to its feet. And on the other end of the carousel was a basket containing the passive kitten. Okay? That's the setup. So for 1 hour each day, they did this thing. And so both the kittens were experiencing exactly the same amount of exposure to light, to vision, to movement even. But the active kitten was in charge and controlling its own movements, and the passive kitten was just along for the ride, right? So at the end of this, the point was to study, are there any developmental differences between these two sets of kittens? And it turned out that indeed, the active kittens had well-developed visual systems, and the passive kittens had very stunted vision, all right? This was a very, very telling result at the time, and it became emblematic of this movement in cognitive science called embodied cognition that holds that embodiment is central to intelligence. There have been many findings in the decades since that kind of verify this claim. Now, my claim is that we haven't quite thought about the role of embodiment in artificial intelligence as much as we should have. And today, our AI or ML systems are still stuck in our 17th century Cartesian kind of viewpoint of the mind. They're still on our screens, right? We still, when we think of AI or machine learning systems, think of them as systems that live in our computers and tell us whether a web image is a turtle, for example, or hold conversations with us purely on our screens. It is non-physical, it is trained with no access to the real world, and it doesn't directly impact the real world. And so I want to instead think about how we can bring AI into physical systems that move around us and can interact and exert forces on the real world. And that's the move from disembodied AI to embodied robotic systems. So I want to think of it in almost an evolutionary sense as going from little primitive AIs that live in our screens to instead machine learning systems that can actually function on robotic hardware. So one question you might ask as a pragmatist is, what does this actually bring beyond this kind of connection to natural intelligence? Why would robots benefit from AI? And then it becomes necessary to look at where robots succeed and fail today, right? A lot of the successes of robotics today happen in the kinds of settings that you see on the left. Process automation settings in controlled factory automation kind of setups, where everything is already pre-controlled in advance, and largely the role of the robot is to repeat almost exactly the same movements every time. There's not that much sophistication happening in terms of how it's being controlled. What you have on the right, if you're wondering, is a road intersection. There's nothing robotic about it. It's a road intersection in Mumbai, and you'll see if you follow some of those pedestrians, like that backpacker, very nonchalantly crossing this intersection. I mean, this is, I think of this as the kind of chaos that trips up robots, an extreme example of the kind of chaos that trips up robots, and of which small portions are present in our daily lives, in our homes and offices and hospitals. And the fact that that human can handle it, whether or not they should handle it is another question. But the fact that that human can handle it tells us something about the kinds of abilities that we have that robots clearly don't have. So robots today do not exist around us in our homes and offices and workplaces, not to the extent that we would like, not beyond a simple vacuum robot, for example. And the background to that is that most robots today are controlled with systems that, to a first approximation, are basically people writing down programs about how this robot should move in the world, right? This works for simple robots like this, but it doesn't really work when you start thinking about this broader problem of deploying and scaling robots to unstructured settings. And so I eventually want to have general-purpose robots in settings like homes and offices and farms and hospitals, and there are many, many challenges involved. One that I'll highlight today in this talk is simply the fact that there are so many things to do in all these settings. It's not that we are doing one specific thing, like the robots that you saw on the previous slide. It's not that each robot is assigned one very specific task and one very specific sequence of movements. It instead has to do so many different things for a robot to be functional in these kinds of settings. There are just so many different tasks, and each of those tasks is also individually harder than the kinds of tasks that we were talking about earlier. So this demands a very different approach to how we think about building robotic systems. It's hard even to foresee and pre-program all the possible skills that a robot might need, right? And so we are thinking about how we can learn, how we can teach robots, essentially, how robots can learn from human teachers. So this requires very fast, flexible, and simple methods where end users in very different settings, you in your home, me in my laboratory, we all can teach our robots to do whatever we want them to do to assist us in those specific settings. And one good way to think about this is to think about how we teach our pets, our humans, to do various things. How do we learn? This is a particularly impressive example that I often bring up of a toddler imitating the famous Rocky Balboa training montage. And he does really an excellent job at this. Like, honestly, this is just amazing, right? But that's imitation. That's one very common way. This is one very common way in which humans learn. Another common way in which biological organisms learn is reinforcement. So if you've trained a pet ever before using a clicker or using a treat, the idea is to reward the kinds of behaviors you would like them to repeat and disincentivize the kinds of behaviors you'd like them not to repeat, right? Another kind of way that you might think of teaching somebody is instruction, where you assume that they already have the basic skill set and they just need to figure out how to put them together in some sequence. And that's one more way of teaching a physical skill to somebody, right? And you will see in today's talk that we are going to adopt all of these different styles of approaches for teaching robots various things. And really, that's what the field of robot learning is setting out to do. How do you get robots to acquire skills from training experiences? And the idea is to develop a unified kind of repertoire of techniques that are not limited to any one specific kind of hardware. So we in our lab work on quadruped robots, but also on hands, and also on robot arms, also on quadrotors. We're not limited to any one set of sensors, any one specific kind of experience. Instead, we try and make use of all of these to the extent that we can. Yes?
You listed on the 3 different ways that you can learn: imitation, reinforcement, and instruction. And you can take this we can take this offline if it makes sense. But I'm curious, are there are there types of tasks or types of things that are best learned through one of those three ways?
Yeah,
right?
definitely. And I'll touch on that somewhat later in the talk.
Very good.
There are definitely some things, so maybe to give away some of the punchline from later in the talk, but it's nothing amazing. But the insight is very simple. You cannot learn through imitation what other people don't already know to do, right? And so if you want actually for robots to be learning skills that are entirely new, and you'll see some of that today, like that quadruped that will walk on a yoga ball, which the video will play later, then those are things that we don't know how to imitate, right? We don't know how to demonstrate for somebody else to imitate. And so the robot has to learn through some other means. Good. And so the end vision is that human end users, without any expertise, will be able to train their robots to do whatever they care about. All right, so let's see some examples of imitation learning. This is always a hit video, and it already got a laugh, so I'll not spend that much more time on it. What should we imitate? All right, what do we actually imitate? We should imitate any demonstration of the kind of behavior that we would like, but in the field of robot learning, we've largely been restricted so far to robot demonstrations. This literally means that somebody is actually puppeteering the robot to do the kinds of things that you would like the robot to do. So in that example on the right, you have kind of like a voodoo doll version of that robot that you're controlling with your arms, and the movements are getting relayed to the robot. In the one on the left, which Liang is controlling, Will is one of the students that will demonstrate on the robot later today. And he's controlling, with a VR controller, the robot arm to perform some kitchen tasks, right? These are examples of you actually taking control, commandeering the robot to perform the kinds of movements that you would like it later to learn to perform by itself. And once we have that, then the task becomes very simple. It's the kind of learning that we've all become quite accustomed to over the last decade or so, supervised learning. You have labels, essentially, for how you should move in response to any situation that you observe in the world. And that's not that different from looking at an image of a turtle and then labeling it as a turtle, for example, right? And so the same techniques can then be used in what's called behavior cloning in robotics, where you might say, looking at that particular version of the scene, clearly the right thing to do is to move my fingers down, for example. And that's really all that's going on there. And so you typically get tens of demonstrations of the kinds of behavior that you want, potentially a couple of hundred demonstrations, and then eventually train what becomes the policy that gets deployed on the robot. This is perhaps the most mature set of techniques that there exists in robot learning today. If you know how to commandeer the robot and then teach it how to perform a particular skill, demonstrate how to perform a particular skill, then you can use that as experience to train the robot. Yes.
I'm most interested by the tens of that's a very small, broadly speaking, data set. Is this kind of, how small is the scope of the action you want the robot to take? I guess, what's the scale of training data to what it's able to do?
Great question. So you'll see also over the course of the next few slides that a lot of the behaviors that we're demonstrating in these kinds of methods is behavior that's very restricted to one specific robot, one specific scene, one specific set of objects that the robot is playing with. So when I talk about tens of demonstrations, I'm talking about fairly short horizon skills, the kinds of skills that would take you 10 seconds, 15 seconds to perform, and in a very specific setting. So if you want a robot to cut an eggplant with your knife on your tabletop, that's one skill. And that will take a few tens of demonstrations. To actually get it to then generalize to my kitchen or my laboratory will take much more. And we actually don't have methods that do that very well just yet. But great question. So one of the things that we've done recently to try and make these kinds of methods better is by changing upstream, before we even get to the supervised learning part, how the robot represents the scene. And we've found that it's really useful for the robot to know what task it's performing to figure out what representation to build of the scene. So for example, if it knows that the task that it's trying to perform in that scene on the left is to put the kettle on the stove, then it is a good strategy for the robot to adopt to highlight those important regions in the scene, to first figure out where the kettle is, where the stove is, what are the different components of the kettle and the stove, highlight those regions in the scene when it builds its representation, and then all the rest of the scene is kind of represented as a hazy background at a much more coarser level of resolution. And the advantage of doing this is that your robot is now no longer affected by potential distractors in the rest of the scene. So if the color of the table changes or something like that, then ordinarily the robot would have been distracted even by such an inconsequential change. But by forcing the robot to only learn policies as a function of what really matters, you get away from these kinds of shortcomings of robot learning techniques. And we find that you can use these kinds of things to learn lots of simple skills robustly. And because they are robust, they don't just run one at a time. You can chain them afterwards into a recipe where you could say, for example, that I want to now prepare an eggplant. And preparing an eggplant consists of performing a particular sequence of actions where you'd first put a kettle on the boil, and then you'll pick up the eggplant and move it into the sink and wash it, and so on and so forth. And all of that can work right out of the box without doing anything particularly special, now that you have skills that are each robust and attentive only to the particular regions of the scene that matter. So this is an example of kind of simple imitation learning, directly mimicking the kinds of behaviors that were demonstrated. And we can get it to do all kinds of other things, like folding a fairly intricate series of folds on a little tablecloth, and then in this case, racking a bowl after pouring some fries into a microwave, and so on and so forth.
Just a quick question. What's your assessment of, oh, sorry, on your right. On your right.
Okay.
Yeah. What's your assessment of how companies like Figure One are performing on tasks like these so far?
It's kind of hard to tell because a lot of these companies are largely releasing demos without necessarily telling us exactly what they're doing. And it's hard to tell. With machine learning systems, it's often difficult to know what is the level of generality that the system is performing at unless you see the experiments across a variety of settings. But there are certainly some quite impressive demos, kind of roughly in the same spirit as things like this, largely automating kitchen tasks and so on and so forth. It's hard to tell whether those skills are actually generalizable to other settings beyond the ones that they were trained in, because the methods that are used, to my understanding, and to the extent that they've told us, are largely similar methods to these kinds of teleoperated demonstrations. OK. As I was kind of foreshadowing a few minutes ago, thus far we've only looked at behaviors that are demonstrated on the same robot, in the same scene, with the same objects. And it would be nice to be able to extend these kinds of imitation learning approaches to beyond just that limitation. So could we learn from more general, diverse, larger sources of data? And one thing that that toddler was able to do by looking at Rocky Balboa on the screen was perform tasks with the toddler's own embodiment that was very different from Rocky's. And so indeed, we could consider that same question. Can we look at human videos, of which there are so many already on the web, and use that as a repository for learning skills that can then be played out on the robot? Our first approach to this was to say, let's still stick to having a lot of actions demonstrated on the robot, because after all, the robot actions are what are going to tell the robot exactly what movements to make. But we will add the human videos as a way to provide some feedback that allows us to focus on what the right exact movements are, what are the more optimal movements among the robot demonstrations, and what are less optimal movements, add a little more nuance to the demonstrations. So we would use thousands of videos to learn a model that would provide feedback to the robot while it was training from the robot demonstrations to figure out which of the movements were more optimal, less optimal, and in that manner kind of do a more nuanced version of imitation. And indeed, we found some gains from doing this. We were able to reduce the number of demonstrations to, in this case, only about 20 demonstrations and get really good performance for a variety of skills that would normally be recognized as hard in this domain, like folding a towel, for example, is kind of a fairly nuanced task.
So I have a question.
Yes.
It started out as a joke, but now I'm thinking it's a real question. So I don't know about the rest of people, but YouTube is my go-to place for how to fix everything, right? Every repair I need to do. I'm always seeing robotics that are kind of at this level. Open the drawer, close the drawer, pick up a thing. What's your estimate about how far are we, if you can use YouTube to train them, to have them do all this kind of repair, dextrous manipulation repair tasking?
I would say we're still a far way from that, but over the next few videos, maybe let's talk about this again after a few slides from now, when I'll talk about one of our first attempts to actually do something like what you're talking about, which is literally learn only from YouTube videos to teach a robot, right? So so that's indeed the question that I'm asking here. Can we get rid entirely of robot and scenario-specific demos and instead learn purely from human videos? And that would give us the ability then to learn policies without any specific reference to one robot, one scene, one object. You could then download the policy that I trained in my lab and run it on your robot, for example. This is actually very, very recent progress. We literally wrapped up the manuscript on this about a week ago, and I'm really excited about it. So this is the first time I'm talking about it. And the idea is, yes, we can actually do a surprising amount with just human videos. What we do is start by looking at how humans are moving about in 3D. For this, we use sophisticated computer vision approaches, the state of the art in understanding 3D. So we take a video, and from just the movements of the camera over the video, you will see this is a head-mounted camera. From the movements of the camera in the video, we get some information about the depths of various objects in the video. That helps us build kind of a coarse 3D map on the left, which tells us where in the 3D world these various objects are located, even though we're only seeing a 2D video stream. And then we can use hand detection approaches. Again, kind of these approaches have gotten really good over the last few years. So we decided to see what we can make of them. And it turns out that you can actually take hand detection approaches in 2D, put them now into 3D, and now we have a good sense of how this hand is moving about in the real 3D world. That gives us a notion of action labels, the kinds of things that we want our robot to eventually imitate. And once we've done that, we can train essentially policies, pretending as though we're training policies for human arms. If we had control over the human arm, how would we move in order to accomplish the task? And that's indeed what you see on this slide. So given a task like opening the drawer on the left, the series of arrows is telling you what your model is predicting the set of movements should be in order to open the drawer. And we find that we can do a fairly good job. So far, so good. Similarly, for open cupboard, given that initial input image, the model tells us what is the sequence of movements that the human should perform in order to open the cupboard. And so far, so good, right? And now it turns out that if you engineer things the right way, and I'll not talk about the nitty-gritty of exactly how we do this, but if you engineer things the right way, you can essentially retarget the movements of the human arm onto the robot arm. And this does really a rather good job. So here is a set of various skills that we've learned using this approach. So you'll see that each of these gray boxes is the name of a skill. We have different variants of the opening skill for things that can be opened by sliding, like a drawer, and things that can instead be opened by a hinge, a vertical hinge. So we have a vertical hinge opening task, and similarly for closing, et cetera. This is kind of one set of skills that we have. We have many more, right? Because human videos now demonstrate so many different skills, we can start isolating many, many different kinds of behaviors into skills like pouring and stirring and so on and so forth.
So over here,
Yes.
sort of following up on her, I love this stuff, don't get me wrong. But, I noticed you didn't open the dishwasher.
Didn't open the dishwasher?
In the previous one.
Yeah.
Because that's a much more complicated task than any of the other two, since it requires a combination of those previous skills. Have you looked at that kind of
Yeah, I think the primary complication with opening the dishwasher would be that it's actually a heavy object, and we don't currently have on the robot that we're working with, we don't have the power necessary.
Well, but it's also, you would have to do, it's actually a combination
Yes,
of
okay,
a
yeah.
set of
So depending on the kind of dishwasher, yeah. There might be additional things that you need to do. And one of the things that we haven't done, and all of this, we are kind of like learning from human videos and targeting a completely different embodiment in the form of the robot. This is really a first attempt at it. We are only able to do a coarse job, and we are to some extent limited by the fact that the embodiments are so different that not everything that you can learn from a human about how they might move their hands, their fingers, for example, can be translated to a robot that only has these two grippers and very limited degrees of freedom on it. But we're hoping to kind of translate more of what we can learn from humans onto robots soon.
Yeah, my question in that regard, sorry, you're
Yes.
left, was, is there any feedback sort of back up the arm? If you pick up a paper cup,
Yes.
you sense right away, is it like completely solid? Is it a little...
Great question. There is feedback. All of these are what we would call closed-loop policies, and that we are, at every moment in time, reassessing the scene and then figuring out what next actions to perform. Now, in this case, we are learning purely from videos, which means that our policies are only accessing visual data. So there is no way for the robot to learn anything about what it should do in response to a tactile sensation. If it finds, for example, that the cup is hot, or that indeed the cup is too fragile to be held with the amount of force that it was applying. There is nothing that the robot can do in response to this that we could have learned from the human videos, because we have no access to information about how the human was feeling when they were performing those tasks. We can only see the visual appearance of the human as they were performing the task. Does that make sense?
Yes, very much. There was another example earlier where it tipped the fries into the plate and, one of them bounced out. As a human, you kind of know to anticipate that possibility, so you tip it gently. Whereas the robot, if it's just mimicking the movement, it's just going to dump it in.
Well, the movement, if it is demonstrated gently, could also be imitated gently.
Okay.
But right now, the techniques for doing that are not very sophisticated. So we used at least a kind of coarse version of the technique, and we didn't kind of pay too much attention to it. But that's a good point. It would indeed be appropriate for the robot to kind of learn how rapidly or how slowly or how cautiously it should proceed in various circuits.
I'm just curious, because you were making the comment about the difference between 5 fingers and the grippers. Have you looked at whether you could also use occupational therapy, like training videos for people who have simple prosthetics?
That's interesting, yeah. It's funny that you should mention it, because the field of robot learning certainly has been thinking, robotics broadly has been thinking about occupational therapy style test beds as a way to evaluate how much we are advancing. Are we able to do things that somebody who is just beginning to recover and it's kind of like a graded version of the task where the difficulty kind of like can be graded over time. And so it is indeed a nice test bed for robotics. But we haven't looked at training from those videos. That'll be an interesting thing to do. Yeah. So the idea is that we can kind of take a few hundreds of videos of humans from the web, and we can train a repository of skills. We're training essentially a skill library. And although I'm only showing you examples of those skills being deployed in our lab, on our robot, with our objects, but none of these are privileged in the training process. It's not that we ever trained with respect to this particular robot or our particular lab. And so we expect that we would be able to download these set of policies and deploy them in entirely different scenes. And there is work on that that's in progress. It's very, very nascent work, right? And so we are now kind of like growing out the skill library over time. We're hoping to kind of make this into a large library of skills that you can then download onto whichever robot you care about. So the punchline over here is that it is surprising how much we are already able to do with our limited techniques for learning from human videos, but there's a long way to go, like many others have pointed out. Right?
I have a question about the retargeting.
Yes.
When the robot has a clasper, it'll retarget the hand that sees in the video to the clasper, which is outstanding, I think. What happens when it doesn't have a clasper? What does it think about retargeting? Yeah.
When it doesn't have grippers, right?
Right, yeah.
Yeah, it's in general the question of how to map between two very different embodiments to achieve some kind of mapping between the action space of one and the action space of another, such that you're achieving the same kinds of things in the world. It's a very hard problem. Indeed, it might even be the case that there exists no such mapping. So for example, if I have a 5-fingered hand and I'm flipping a pen, you have no way of replicating that same behavior just through the constraints on your embodiment if you only have a 2-fingered gripper and limited degrees of movement. So there are no good solutions to this broad problem just yet, even in terms of constructing the best approximate mapping from one embodiment to another that I'm aware of. Yeah. Good. So what about tasks that we don't know how to perform or easily demonstrate, like I was asking a few moments ago? So all of this is based on being able to see other people or see the same robot being controlled by somebody else, and using that to then learn some behaviors. But what about the kinds of things that we don't already know how to perform or easily demonstrate? And this is where we start looking at methods that do reinforcement learning instead, right? You'll remember that reinforcement learning, I told you, was kind of broadly inspired by the ways in which we teach animals various skills. So we would, for example, I hope the stage isn't falling apart, but we would broadly, for example, use treats to tell a dog what kinds of behaviors we would like for the dog to perform again and what not, right? And so you can think of it broadly as learning through trial and error. The abstraction that we normally use is of an agent, like a robot, and an environment, which is all the rest of the world except for the robot. And the agent observes the state of the world, what is the configuration of the world, and then takes an action A, let's say, in the world. And in response, once that action is relayed into the world evolves according to some physics, let's say, and in the process reaches a new state S prime. And that new state S prime comes together with a little tidbit of information that we call the reward, which is feedback to the robot about how it should behave and how it should not behave. And the reward is kind of like that treat that you would give to a dog. So the rewards are guide the agent to learn through task and through trial and error, right? So the only way that the robot knows what it's supposed to do and what it's not supposed to do is by looking at these reward signals and figuring out whether those are going up or down, right? Now, a problem with trial and error learning, if you remember how you first learned to ride a bike, for example, this takes a lot of experience to generate complex behaviors. And it's also fairly unsafe. There's a lot of falls. Our robots are fairly expensive pieces of equipment. We likely don't want to be spending many, many days on the robot. We don't want to break them many times. And so instead, we train them in simulators. This is largely the method that the robot learning field has come around to, that reinforcement learning needs to happen in simulators. We have, fortunately, many fast parallel simulators that run on the same kinds of hardware that our video games and now our deep learning models run on, GPUs, that permit really fast parallel simulations of approximate physics. So these are examples of many, many different robots that are essentially being trained in parallel to gathering experience in parallel. And so we can get lots of experience, the kinds of experience you couldn't dream of in a real robot in the simulated setting. It's going to be approximate experience. It's not going to be exactly faithful to the physics of the real world, and so we'll need methods to take care of it. But it gives us a really good starting point in terms of making lots of experience that we can learn from.
I don't know if you were here yesterday, but we saw a little video of somebody trying to learn how to ride a bike when the handlebars were reversed.
Oh, I see, okay.
But I suspect the robot using this technique would do a whole lot better than I would.
Yeah, I think so too. And the logic comes from the fact that the robot is learning, in this case, from scratch, not with any preconceived notions of how a bike would steer. So whether or not the handles are reversed is basically, it's irrelevant to the robot's learning difficulty for the task. Yes.
Yeah, I just want to do a time check because I know we've got the demo still to do, and we just have 6 minutes.
Yeah, I'm almost done with this set of slides, and yeah, we can go into that very soon. So one approach that we use here is sim-to-real RL, like I said. And in the process of sim-to-real RL, there are typically many, many decisions that need to be made by a human designer, a human who is actually looking at the behaviors of the robots that are generated, and then in that process, kind of engineering the reward function to get better and better behaviors over time. And what we've recently done is we have automated this using ChatGPT and similar kinds of models, large language models that are able to generate for us the pieces of code that a human engineer would need to repeatedly, iteratively tune over many weeks typically, and instead do it in 2 days of compute on the cloud. And we are completely training the entire policy in simulation to achieve really, really hard skills, like this example of a quadruped walking on a yoga ball, right? And so you will see here some examples of transfer from pure simulation to the real world.
Question on you, right?
Yes.
Would it learn if it did fall off what it shouldn't have done?
Yes.
Or should have done?
Yes. So the reward function has the reward, basically the reward signal is responsible for communicating to the robot when it did a good thing and when it did a bad thing. And so, for example, falling off in the reward function would be penalized heavily. And so the robot would learn that this is not good behavior. So here are examples of robot skills that are trained entirely in simulation transfer to the real world. We were very proud of these results. We took them out. You'll see Hangju Wang, who's not able to be here. We took them out onto the streets of Philadelphia, all around the Penn campus, and tested the ability to work outside of the lab settings. We have here some examples where we were brave enough to, rather than having Sam Wang, who you'll see shortly, wrangle the robot, instead kind of let go and see how far it could go without him holding on. And here are some more examples of the robot and us being mean to the robot. So we kick the robot around, and it still manages to balance fairly well. We've been even meaner to the robot, where we started removing some air from the yoga ball and inadvertently kind of did this thing. We weren't really intending to do this, but the robot seemed to manage just fine, right? And here is perhaps a sneak peek at our most recent result, which is that we've managed to get this robot to do more complex things, like walking over an obstacle course by training it automatically in simulation over a curriculum of increasing difficulty of obstacle courses that also incorporate now the yoga ball as well. So we're having a lot of fun with this quadruped robot right now. And with that, let's see a live demo from Will and Sam. So these are Will, Liang, and Sam Wang, who are both undergraduate students at Penn. Penn undergraduates are just amazing, by the way. When I think back to where I was as a roboticist, as an undergrad, I could do hardly a fraction of the kinds of things that these kids can do today. So we can keep that running in the background over the next couple of slides, and maybe just pause it, Sam, for just a couple of seconds. Can I ask you? And then after a couple of slides, you can keep it running while I take questions, and then we will also have the robot demo continue during the coffee break afterwards, and you can come talk to Sam and Will. So just kind of wrapping up the presentation itself, there's a lot of excitement about robot learning, but I also want to be very upfront and honest about the shortcomings and challenges right now. We don't really have fully general solution approaches just yet. We don't have ways to handle tasks like very dynamic ones, like throwing and catching heavy objects, contact-rich ones, assembly and insertion, the kind of thing that you might think a watch mechanic might have to work on, very high precision tasks in unstructured environments. We don't really know how to do those things very well just yet. And this is largely the reason why there are no really good examples of robot learning that are deployed in the real world just yet. The closest we've come is autonomous driving, and even there, we are not quite there, all the way there just yet, right? Safety, reliability, and trustworthiness are even more of a concern for robot learning than they are for generic machine learning that lives in your screens because of the potential capability for immediate physical harm. There are foundational challenges in robotics. Robotics as a discipline has been around for a long time, but honestly, we don't have good answers to very basic questions in robotics. The kind of questions that I've been asking recently are things like, what is actually the process of converting sensed information in the world to physical work? What is the information that's important to sense? We don't even have answers to very simple questions that you can ask in 7 words, for example. And that gives us some pause about the potential limitations of approaches like this. And we do need to think more carefully about foundational challenges before we eventually scale up these things to the real world. So there's lots of well-founded excitement, but there are also lots of challenges. But don't worry, we're at it, and hopefully we'll solve this in the next few years. With that, I'll thank the crew at my research group, as well as all the funding agencies that have funded our work so far. And Sam and Will, if you would like to, please continue the demo while I take questions. Yes.
So regrettably, we just have 30 seconds here. Jim? Yeah.
Well, so just real quick, the obvious question, having been to many conferences and things like that, and going away from the storytelling stuff, is how does this compare? Because I've seen a number of demos of robot learning. This is obviously a very complex behavior, but I've seen other complex behaviors from other labs.
Yeah.
It's just...
It's a good question and a hard one to answer.
How would we even evaluate that?
It's a good question and a hard one to answer, and one that I think robotics as a discipline has grappled with over many decades, that it's really hard. Unlike in, say, computer vision or anything that lives purely on your computer, it's very hard to download somebody else's method and get it to run on your robot. But we're making progress in that direction. So the kinds of applications that I was showing earlier, where you can literally train a policy on the web and then download it and run it on your robot, that's the kind of thing that I'm hoping will make it possible for the field to have some clear benchmarks where you can say, compared to the policies that Dinesh's lab trained, Here is our policy, which we also train and which you can also download and run on your robot. Because otherwise, we're really generating behaviors that are very specific. This behavior on the quadruped is actually somewhat more general, partly because this quadruped happens to be very popular today, and many labs around the world have it. And also, we're not using any particular visual sensing on it. We're only sensing what's on the, what's already in the joints, in the motors in the joints. And so it doesn't need to worry about the particular setting that we are in. And that's largely the reason that we're even able to demo it here. It was trained only in simulation, but we can do it in our lab. We can do it on the roads of Philadelphia, and we can do it here because it doesn't need to be sensing specifically what's going on around it visually. Instead, it's only relying on the movements that are the sensed movements of its limbs.
Yeah. Fabulous talk, fabulous demonstration. Thank you. We're going to see some more during the break. So.
Awesome. Yeah. Thank you.